Hello everyone, welcome to this talk. My name is Lin Yan, a postdoc from Argonne National Laboratory. Today I will present the paper named Trophy, a topologically robust physics-informed tracking framework for tropical cyclones. This is a collaboration with Hanqi from the Ohio State University, Wang from the University of Utah, and Thomas Peterka and Jiali Wang from Argonne National Laboratory. Tropical cyclones are among the most destructive weather systems. Realistically and efficiently detecting and tracking TCs are critical for assessing their impacts and risks. In the past decades, many TC trackers were developed by research institutes and weather forecasting centers. In this slide, we list some of them. One limitation of these trackers is that most of them require multiple dynamics and thermodynamics variables at different altitudes to detect and track a TC. Many input variables are often not available from raw data and need additional calculations, which can involve handling a big amount of data. Another limitation is that the choices of threshold to detect TCs in these algorithms were generally subjective. Moreover, most of these trackers focus on track the TC regions instead of TCIs. Meanwhile, vector field topology has seen applications in climate science and has potential use in tropical cyclone tracking. Critical points of 2D vector fields, which can be defined as where a vector field vanishes, can be used in tropical cyclone detection. We list 4 types of critical points: source, sink, center, and saddle. The eye of TC can be detected as a center when it intensifies into a strong hurricane with very low wind speed in the eye and extremely high wind speed along the eye wall. It can be detected as either a source or a sink at its landfall. There are also many critical point tracking algorithms that can be further used in tropical cyclone tracking. Here, we demonstrate FTK, an algorithm developed by the co-author of this paper and is used in our newly developed framework. We also want to mention our previous work, the multi-level robustness framework, which is designed for general time-varying 2D vector fields. It shows the potential in tropical cyclone tracking and has advantages include, first, tracking the TCIs instead of the TC impact areas. Second, super lightweighted, require only near surface wind speeds and directions. Third, it is able to work with any TC or critical point tracking algorithms. However, it also has limitations if used in tropical cyclone tracking directly, such as computationally expensive and tracking result unreasonable under real-world scenarios since it is physical information unaware. In this paper, we introduce the Trophy, a topologically robust physics-informed tracking framework, which inherits the capability of the multi-level robustness framework and overcomes its limitations. Now, we use the pipeline of our Trophy to highlight our contributions. First, we introduce a physics-informed feature selection strategy to filter short-lived and unstable features. Such a strategy removes 19% of critical points in the multi-level robustness computation and makes Trophy much more efficient than the previous approach. Second, we propose an adaptive strategy to use physics-informed local neighborhoods for the multi-level robustness computation, making it more efficient and physically meaningful under real-world scenarios. Third, we give 2 feature selection strategy considering the physical properties of tropical cyclones before visualization to reduce visual clutter and highlight dominant features in the domain. Next, I will give some technical details behind our topology-based tropical cyclone tracking framework. First, let's go a little further into critical points. A critical point can be classified with respect to its degree. A source, sink, or a center which can be identified as the eye of a cyclone has a degree +1, and a saddle point has a degree -1. The degree can be used in robustness calculation. So what does robustness mean in our framework? The robustness of critical points quantifies their structural stability with respect to perturbations of the flow, or, in other words, their importance as a feature of interest. We can calculate the robustness of a critical point using a merge tree arising from the magnitude of a vector field. For the time limitation, please refer to a paper for the technical details of robustness calculation. For this example, x1 and x2 has robustness equal to 0.65, and x3 and x4 has 14.7 as its robustness. These results suggest that it is easier for x1 and x2 to be cancelled with each other than x3 and x4. Now we give the vector field from the same dataset, but a one-time step behind the vector field in the previous example. We see x1 and x2 disappear, whereas x3 and x4 remain. Both degree and robustness of critical points can be used in feature selection. We use this strategy to filter critical points that are short-lived and have low stability, thus preserving good candidates for tropical cyclone tracking. This slide shows FTK critical point tracking results for an ERA5 dataset in 2004. It contains more than 100,000 critical points and 20,000 tracks. Our goal is to select a subset of tracks for the following processing. Consider the physical properties of real-world cyclones. We incorporate two rules in physics-informed feature selection. First, since the duration of a tropical storm or cyclone is usually larger than 1 day, we require the selected tracks to contain at least one one-day segment that consists of +1 degree critical points only. Second, since a critical point representing the center of a cyclone usually has high stability across the time before it hits the land and dissipates, we require the segment detected from the previous step to have high average robustness value. With these two requirements, the number of critical points and tracks decreased to about 10,000 and 86 respectively, which means only 9.5% of critical points will go into the following process of our framework. The next step for trophy to track tropical cyclone is multi-level robustness calculation. We need to know what is multi-level robustness and why we need it first. The classic robustness is calculated with a single tree arising from the home input domain. It suffers from undesirable boundary effects. Multi-level robustness aims to find the smallest possible amount of perturbations to the vector field necessary to cancel each critical point. It can be calculated as a sequence of robustness values computed from its neighborhood of increasing radii. The right figure shows how the robustness value changes with respect to the increasing radius of the neighborhood for critical point x. Cancellation partners of x are rated in bubbles in the left figure and are colored by their frequency as partners. We can see many cancellation partners of x are far away from x, even if it can be cancelled with y within a 6-degree region under a 1.6 perturbation. The cancellation between remote partners are mathematically justifiable, but it is almost impossible to happen in real-world scenarios since no perturbation could happen across the whole Atlantic Ocean. So, we impose constraints during the multi-level robustness computations to focus only on physics-informed neighborhoods of tropical cyclones. First, we set a neighborhood size where real-world perturbation could happen. We set this radius to be 10 degrees since hurricanes are among the most destructive real-world perturbations to wind fields and are typically about 4.7 degrees wide. Then, trophy consider all possible cancellation partners within this neighborhood using varying radii. Now let's go to the final step before visualization. We have 3 feature selection strategies to help users reduce visual clutter and highlight the dominant features in the domain. The first one is a stability filter, which is inherited from the previous work. It captures the average point-wise stability and the lifespan of the track. The second feature selection strategy is referred to as the maximum wind speed filter. Since the stone systems are usually categorized by hurricane's maximum sustained wind speed, we use these filters to control the categories of stones that users want to visualize. The third one is the smoothness filter. It is used to filter out tracks that are too tortuous to be considered as tropical cyclone tracks. We give 2 strategies to choose the threshold for these 3 filters. The first one, which is referred to as default, can be used if we have certain references. It uses values when the density patterns from trophy and the reference have the maximum Pearson correlation. The second one involves human-in-loop. It allows users to fine-tune these values independently for individual tropical cyclone tracks of interest. Next, let's see some experimental results. Here is an overview of experimental details. We present experimental results using a 30-year near-surface wind vector field from the EI5 dataset. We use IB tracks as reference. IB tracks are observations reported by WMO forecasting centers. We also include the TC tracks result of tempest extreme for comparison. We use the frequency, durations, intensity, and so on as evaluation matrix and conduct experiments on case studies and statistical evaluations. For time limitations, this talk will not cover all experiments. Please refer to our paper for all experimental results. Here are TC tracking results for 2004 to highlight the tracking differences between different algorithms. The main difference between Tempest Dream and Trophy is the highlighted tails. Since Tempest Dream requires both dynamics and aerodynamics variables to meet its specified criteria, it usually cannot detect the beginning and the endings of TC while the wind speeds are low. Trophy can detect such tails as long as the centers of the flow can be identified as critical points. However, Trophy does not always have longer tracks than Tempest Streams. We now investigate a Category 1 hurricane named Hurricane Lisa. We can see that the track detected by Trophy is clearly shorter than the other 2 methods. Taking a look at the vector fields, we see that the eyes of Hurricane Lisa were detected at center only up to August 8, 0 a.m., after which Hurricane Lisa lost its distinct eye and cannot be detected by Trophy. Such a process could be related to extratropical transitions of tropical cyclones, which may occur as Hurricane Lisa moves over cooler waters and into areas of strong wind shears at higher latitude. During this transition, the cyclone loss is symmetric and distinct eye, and thus Trophy terminates its tracking. Next, let's see some statistical evaluations. For annual climatology, statistics are calculated over the entire data period, which are then normalized to a per-year basis. The first column shows the annual TC counts. IB tracks contain about 11 TCs per year within the studied region, and the Trophy with the default setting produces the least number of TCs. However, if we look at this example, because Tempest Extreme requires different variables to meet specified criteria, TC tracks may break into pieces when some parts of the track do not meet the requirement. Trophy can detect TCs not only during their movement, but also at least partially during their formation and dissipation periods, even if their wind speed is low. This is consistent with what we observed in the second column, where trophy produces TC tracks longer than tempest stream. The last column shows the latitudes of lifetime maximum intensity. We see both trophy and the tempest streams shows a powered basis compared with IB tracks. One possible reason could be that the realistic data, including Jiali 5, are not able to simulate stone structure near the equator well, indicating that the input data to any tracking algorithm is the most important factor when studying TCs. Trophy has a number of limitations, such as our framework is not suitable for asymmetric feature tracking such as extratropical cyclones. Second, to obtain optimal tracking results, we may need to fine-tune the parameters for each single event. Third, the current framework only considers near-surface winds. However, higher altitude winds are also a big concern when it comes to real-world applications such as wind energy. Extending trophy to utilize 3D data for TC tracking is one of our future works. Finally, I would like to thank our funding agencies, and thank you for listening.